For this first question 5e, we are given a curve y equals to xy and a straight line x equals to 1 over 3. So the double integral, we can just substitute 0 until 1 over x, 1 over 3, and 0 until x squared. And then just integrate it. There's no special technique over here. Just increase the power and divide by the power. And the position of dy and dx can be swapped, means dy can be written into dx and dx can be written into dy. But if you swap the position of dy dx, the letter or the symbol over the integral also must be changed. For example, the x squared must be changed to y squared if you change dy into dx. And the final answer also will be the same. Just integrate, do the double integrate, and then the final answer you will get is 17 over 4,860. Question 2.5f, we are given a condition that you have to find the area bounded by the circle and the straight line in the first quadrant. So actually the double integral should be 0, 2, and 0, y, because if you follow the question, the shaded area will be between the straight line and the curve toward the direction of the y-axis. But as I say in the previous example, in the previous manual calculation, if you change the dy and dx, the position of them, you will still get the same answer. So in this manual calculation, I changed the position of dy and dx. Also, I changed the letter of the y. So originally it's supposed to be 0 until y. I changed it into 0 until x. And then dx, I change it into dy. And then as you can see, I show the calculation. Just integrate normally, increase the power and divide by the power, and then substitute the value. You will get 4 over 3, which is the same answer if you do it with dx then dy. So for the last question, we are given three lines, y equals to 2x, x, and y equals to x, and x equals to 2, and we have to find the area bounded by these three lines. So what we can substitute into the double integral is x until 2x and 0 until 2. And since this question, the z is equals to y over x squared plus y squared, and then for dA, it actually can be dx and dy or dy dx, but I prefer dy dx because the integration have one special property. If the numerator is similar to the derivative of the denominator, you can use ln. So in this case, if we add 2 on the y, it will be looks like the derivative of y squared if respect to y. So to make this easier, I prefer to integrate with respect to y first. So I add 2 on top of the y, and then to cancel out that 2, because originally it doesn't have a 2, so I have to put 1 over 2 to balance it out. If you integrate with respect to x first, you will get arc tangent. So this one is very complicated. By referring to the module, you can see the answer it suggests is ln. So it's obvious integrate with respect to y will be a better choice. So just integrate it, and then similarly after integrate it with respect to y, just increase the power and divide by the power, and then you will get the final answer ln 2.5.
And now I will present about the graph sketching of the manual calculation. This is the question 5e, and from the question we know that the region R is bounded by y equal to x squared, uh, x equal to 1 over 3, and y equal to 0. So this is the production of the information given. And this is the graph of the question 5f. There is two function given, which is y equal to x and y square plus x minus 2 square equal to 4. And the region R is bounded by these two function in the xy plane graph. And the y square plus x square graph is the function for the circle graph in the graph. But since x is x minus 2 in this function, hence the whole circle is shifted to the right side in two steps, and the central point of the circle is coordinate 2 0. And now this is the graph of the question 5G. And from the question given, there is three line which bounded the region R, which is y equal to x, y equal to 2x, and x equal to 2. And we can see that the region R is a triangle shape in this graph.
Now we're moving on to calculation by software. So for question 5e, first we define the integral bound, which is x min and x max. So and then we define the integrand function. So in MATLAB I use integrand equals to alias x comma y in bracket x plus y semicolon. So this define the integrand function. The alias symbol is used to create an anonymous function in MATLAB, which allows us to specify the function directly in the code. So third, we set up and evaluate the double integral. So I use result equals to integral 2, then integrand, comma x min, comma x max, comma the other two terms, which represents the y equals to 0 and y equals to x square respectively. And lastly, I write according to display the result. Okay, now for question 5e, first I define the function and region. So f represents the integrand function, R1 represents the upper boundary of the integration region derived from the circle equation centered at 2 0 with radius 2. And then R2 represents the lower boundary of the integration region, which is the line y equals to x. And then I set the integration limits. So x min and x max define the range of x value over which we perform the integration. Here x range from 0 to 2. The point where the line y equals to x intersects the circle. And then point y min and y max define the range of y values. Each x y min is given by the lower boundary y equals to x and y max by the upper boundary, the circle equation. And then third, we perform the integration by using result equals to integral 2 in bracket f, comma x min, x max, y min, and y max. This line use MATLAB's integral 2 function to compute the double integral of f over the defined region. Integral 2 takes the function f, the limits for x from x min to x max, and the limits for y from y min to y max. And then lastly, we write according to display the result. Okay, for question 5G, first we define the function to be integrated as usual with the two previous question. We use alias to create a function handle. Second, we define the limits of the region, which is x min and x max, the limit of integration for the variable x. And then y min and y max are the limit for integration for the variable y. And then third, we perform the double integral, which is result equals to integral 2 in bracket f, x min, x max, y min, and y max. This line use the integral 2 function also to evaluate the double integral. And lastly, we write the coding to display the result in so we can display the result.
So this is the graph sketching for simulation. So for the simulation, I'm using the Maple software. So for the question 5E, first we must define the function, which is f to the function x and y is x plus y. And second, plot the graph. So these are the coding that I insert, and this is the graph. So as we can see, I get same as the manual manual sketching. Moving to the questions 5F. Uh, so the first command, we must define the circle and the line. So we can draw the circle and the line by using this coding. So and the second one is intersection point. The third one is region sketch. Uh, this region I do it by manual because I can't get the region shaded region. So I just do the manual. So for the fourth one, polar transformation and integral, I just use this coding. So for the last one, integrating listing polar limits. So the result is the next one, the right one. So for the last question, which is 5G. So as usual, starting with the with plots, and the first one is define the function. So why this is the coding, this is the equation. So for the second one is define the region. Region is region to the sketching, to the shaded region. So for the last one, plot the function over the region. So I use this as a I use this I use I plot this graph with 3D because I want like different scaling, but still it will give the same result as I do the 2D graph. So the right one is the result.